In the previous video, I talked about mechanical work in very general terms, but to at least illustrate or give more of a concrete idea of how mechanical work will affect the energy balance, I want to go over some specific sort of scenarios or specific examples of mechanical work. So examples of mechanical work. And the first example we're going to go over is the case where we have quasi-static isothermal expansion. And so isothermal, that's a word you've seen before. That just means that temperature is constant. Quasi-static, that might be a new word for you. All right, and so really all that means, if you have a quasi-static process, that just means the process is carried out so slowly so that the system remains in equilibrium throughout. All right, and that's going to be important because when we start applying things like the ideal gas law or more complex forms of pressure equations, all those equations are going to be only applicable for systems that are in equilibrium. Okay? Alright, so we'll go into more detail about that later, but for now, all you should focus on is that quasi-static means that the process is carried out very, very slowly. Alright? And so with a quasi-static isothermal expansion, what has to happen in order to keep the temperature constant as the gas is expanding, heat needs to be added to the system. And so we regulate the value of Q so that the temperature of our system is constant. Okay? Alright, and so if we draw out our piston again, and we have our gas, what we're going to do is we're going to, as the gas is expanding in this direction, we're also going to be adding heat to the system as well. And so in the end, our gas has now expanded to a new X value. But if we compare the temperature of the system in state 1 to the temperature of the system in state 2, we would see that temperature 2 is just going to be equal to temperature 1. Okay? And so that's the premise of the situation. All right, and so for this sort of system, the way we could analyze it is through our energy balance. And so in our energy balance, we have dE is equal to du plus dEk plus dEp. And that's going to be equal to dQ plus dW. Now, for the system, we can make one assumption in which the changes in the kinetic or potential energy of the system, those are going to be negligible. All right? And so what we'll do is we'll just assume that these values are 0. Furthermore, we could also apply another assumption, which is that the system is isothermal, the temperature isn't changing, and because the temperature isn't changing, and we know that the internal energy of the system is a function of temperature, if the temperature isn't changing, that means that the internal energy won't be changing as well. Right? And so what we're going to do is we're also going to assume du is equal to 0. And that's because it's an isothermal system. And so what that means is that on the right-hand side, we had dQ plus dW. Because the left-hand side is 0, that means the sum on the right-hand side is also going to be equal to 0. We could then just manipulate the remaining terms so that we have dq is equal to negative dw. And then if we took some sort of integral, we would have q is equal to the negative integral of dw as well. Okay? And so that's just what we get from the energy balance. But now, at this point, in order to get a more quantitative and precise understanding of what the heat required for the system is, we could start applying our definition for work. So, from the previous video, we know that in general, dW can be described as the negative of the force exerted by the gas times the displacement caused by the system. From the arguments in the last video as well, we also know that the force of the gas is equal to the pressure of the gas times the area of the piston that it's acting on times dx. Okay? Now, here, we know that nothing about the piston itself, nothing about its properties are changing. So the area that of the piston that the gas is acting on, we could say that this is constant. And because it's a constant, that allows us to just move it around all over the equation. And so what we're going to do is we're going to take that area constant, we're actually going to put it inside of the differential. And the reason for doing that is now, if we have area times displacement, what that does is it gives us a volume back. So now we have P gas times the derivative of volume of the system. Okay? And so now this sort of equation kind of has a more concrete meaning. At this point, I also want to start talking about the pressure of the gas itself. Right? And so this pressure right here, unlike the area of the gas, we're going to say this pressure is not constant. Okay? Right? Because intuitively, as the gas is expanding and as the piston is moving, that increases the volume of the system, and as a result, the pressure of the system is also going to decrease as well. Okay? And so this pressure, it's not going to be constant. But because we're assuming this is a quasi-static system, so since quasi-static, what we're assuming is that the expansion is going so slowly enough that the pressure in our system can be described by using a equilibrium equation of state. So since quasi-static, can use equation of state. And so by equation of state, I mean we could use some sort of equation that relates pressure to volume and temperature. All right, and so one such equation that we're all very familiar with at this point is the ideal gas law. So if we assume an ideal gas, we can use that ideal gas law. Right, and so what we could do is in this dW is equal to negative P gas dV equation, we could replace P gas with the result from the ideal gas law. So now dW is going to be equal to negative moles times the gas constant over temperature divided by volume. All right. And so what we now have here is an equation with volume inside of it. And now it'll be a little bit more easy to manipulate. And so if we go back to our energy balance equation, we have Q is equal to the negative of the integral of dW. And so now that we have dW, we could plug this equation in. nRT dV over V. The negatives will cancel, so we could not have to worry about that. We could also pull out things that are from the integral that are constant. All right, and so here we know the gas constant is a constant, so we can move that out pretty easily. The number of moles in our system, are constant as well because we're dealing with a closed system. What's also constant is the temperature. Right? We're dealing with an isothermal system, and so that means that the temperature in our system is going to be constant as well. So we could pull all those things out, and what we have now is nRT, and then the integral of dV over V from some volume 1 to some volume 2. And the bounds of the integral also changed, right? Because instead of just dealing with x, we're now dealing with volume. Okay? All right, so we could integrate this. So if we integrate that, what we get is nRT times the natural log of volume 2 over volume 1. All right, and so now we have this direct relationship between the heat added to the system and the volume of the system as well. And so this is going to give us insight into, what the sign and what the direction of the heat is going to be, or are going to be. And so, for instance, if the volume in state 2 is greater than the volume in state 1, we know that the work exerted by the system, by the gas, is going to be negative because the system is expanding. We also know that the heat required by our system in order to keep the system isothermal, that's the opposite sign of work as well. And so if our work is negative, that means the heat is going to be positive. And so heat needs to be added to the system whenever there's expansion in order to keep it isothermal. In the opposite way, if V2 is less than V1, we know that work has to be positive because compression is going on. And so if our work is positive, that means in order to keep the system isothermal, heat needs to be released from the system, or heat needs to be negative in value. And so this is a sort of result, this is a sort of equation that you would get if you were dealing with a quasi-static isothermal expansion.